This is Unit 2, Section 2.2. We're going to look at misleading graphs and then creating dot plots again, more formally than what we did with our Beyonce activity. So our goal today is to be able to represent some categorical data using frequency or relative frequency tables. And this is kind of what we did last time. Describe the categorical data. Again, so we're going to rebuild on some of the things we did before. And then represent categorical data graphically, so pie graph or a bar chart. And then we're going to start to move into our quantitative data. So 2.2 on misleading graphs, it's this idea of, here's a Dilbert cartoon that says, I didn't have anything useful to say, but I made this pie chart. And people are saying, ooh, it must be true because it's pie. And he's thinking to himself, that worked too well. I pledge my life and fortune to the pie. People understand, especially marketing companies and political companies, know how to present data in a way that could be misleading or could be representing something that has a bias because they are after something. If you're campaigning for a political party, you might have data that's misleading because it's not telling the whole idea, or if you don't have a basic understanding of statistics, you could be, you could be presenting unreliable data just because it's not created properly. So we're going to look at some of the ways that we can identify misleading graphs, as well as move into taking and making a dot plot as our quickest way of collecting quantitative data. So the first one is, here's a pictograph here, and it's talking about the number of buyers they have, and if their previous computer was, neither a Windows machine or a Macintosh. So Apple versus Windows. And so how is the pictograph misleading? So if we think about our pictograph here, we want to see that this size it's misleading because it looks so much bigger than what we have as far as our data. A bar chart should be the same size bars for every single thing. So when we have a picture like this, it's deceiving when we see a picture. And even though, to a person that's more in visual design or visual arts or into something that's, a little less just a bar, it might be more appealing visually, and it might give that idea of like, oh, these are now computers we're talking about without having to read the labels. But the sizes here of the pictures, that's going to be misleading here, okay? Anytime we use pictures instead of bars, that's misleading because the area associated with it seems to cover a lot more than here. So if I took this idea of here, where yes, it appears that the previous computer for Windows is 100 and this is about 350, so maybe 75 and 350, but it shouldn't be this many that fit into that idea, where it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's not 12 times larger than Windows that people are choosing to now buy Macintosh. That's not the idea that we're trying to convey when we're trying to say it's about maybe 3 to 3.5 times bigger. That's what we're trying to convey. So when the picture brings this in and makes it 12 times larger with the area associated with the picture, that's misleading. So one way that we can correct that would be to make an appropriate bar graph. So taking the data here that was poorly displayed and making a bar graph that says, here's 2 possible bar graphs of the data. Which one would still be considered deceptive? So now we have our percent of people buying. We have the previous computer, percent, previous computer, none, the PC, Macintosh, none, PC, Macintosh. How is this still having, we've converted it to bars, which one of these could still be considered deceptive? Okay, it comes down to the scale. This one starts at 0, this one starts at 10, minimizing that one even further. So again, even though they're cutting off that 10 for everyone, what they're doing is making this look smaller while emphasizing Macintosh. So again, this one is deceiving. So the second graph is still deceiving because the scale doesn't start at 0. And so one of the things that we want to look at is, how are we putting the data out there? Is it true data? Is it organized well? So one of the things that we have to look at, and this is what I'm going to post as a discussion on Canvas, is this article that leads us to a BuzzFeed article with all these graphs that lied to us. And so I want us to make comments about those, or even go out and find your own graph and post that for us so that we can comment on it and say, what's wrong with these graphs? And you'll find them, even if you look, at yesterday's graphs. You could find poor information on coronavirus, on politics, since this is a big year for that. There's things that will lead us to misleading information. And the most common ways that we can start looking for it are misleading the eye with the size of the bar or picture. So size of the bars or using a picture. So this wouldn't get better if we just took the picture away and used bars. If we make this one compared to this one the same width, and then this one is 2 or 3 times larger, that doesn't fix it. We still need to make sure that we're not using pictures and that we're consistent with the size of the bars. We need to make sure that we check the scales, like on the one above where it didn't start at 0. So a common way to make a misleading graph is to not start at 0. Okay, another one would be not using the pie chart appropriately. So this would be where you're not actually comparing to a whole, but you're still writing it in as if you were. So we want to make sure that not all percents lead itself to a pie chart. And this is hard to create well without technology. So we don't want to misuse the pie chart. Some marketing companies, some Word documents, Excel, they make the bars like 3D or too flashy, where it's like, no, we're trying to convey something that should be simple and very straightforward. And consistency is statistics, where we want to see that presented well, consistently, where most people could read it and understand the picture that the data is presenting. Not the picture that you want presented or that somebody else wants presented, but the one that the data is presenting. And then another way to make a misleading graph is to not only have scales that aren't appropriate or not in the right order, but we could be missing scales altogether, where there's just 2 bars and they're trying to make you come up with how large the scale is. And so as you explore this link on the discussion on Canvas, you'll see that all of these are ways that we can kind of check off a misleading graph. The second part of today is looking at creating a dot plot. And so we did this when we did our Beyonce activity with our sampling. Now we're going to make a dot plot by hand here. So a dot plot is when each observation of a distribution is shown. Okay, so each observation is shown. And as a dot plot, above its location on above its location on a number line. So our example, let's make a dot plot of the data on the number of goals scored by the 2004 women's U.S. soccer team in the 36 games they played that season. So the first thing we want to do is create a scale. And so again, this should be A scale that's pretty quick to make and consistent as far as going in order, not skipping things, everything's equally spaced. And then we would go through and plot them. So we would have 3, 0, 2, I just said 3. Whew, let's start over. 3, 0, 2, 1, 8, 2, 4, 3, 5, 1, 1, 4, 5, 3, 1, 1, 3, 3. Should have given us more vertical space here. 3, 2, 1, 3, 2, 3, 4, 3, 4. Whew. And then 0, 1, 5, 1, 0, 5, 7, 1. All right, so as I start looking at this one, there's a couple things that we can do to start describing dot plots. And so as we've switched from kind of our misleading bar graphs here, this is our first look at a quantitative data set. And so dot plots are a quick way to organize smaller data sets that you want to still be able to observe each observation. And so when we looked at this point, this represents one game in 2004, and I could even say this is the number of goals in one game in 2004 by the 2004 U.S. soccer team. And so when we look at this, our data is represented as individuals, not as groups. When we did a distribution for our Beyonce idea, each one represented a sample, not just an individual. So we're going to look at dot plots frequently this year and just be able to start looking at them and creating them quickly. This is a graph that we can't make on our calculator. And so this one, while it's quick to make by hand, if I have a much larger data set or with numbers that are further spread out than this, have more variance or more variability, I might not choose dot plot as my first quantitative display. But for this purpose, in a smaller data set with a small variation only from 0 to 8, this can be pretty quick. Keep in mind that we want to keep our dots spaced evenly. So like 3, 3, 3, 3. I try to make this one a little bit lower because I wanted to show like the difference that makes if it's not consistent. This one should be up higher where that 3 should be consistent all the way across. 4 should be consistent all the way across. Where this dot should be moved up a little bit so that it goes 4 all the way across, 5 all the way across, 6, 7, 8, 9. So we want to try to be as consistent as we can so we start to get an idea of the distribution of all the goals. Where we can say it's pretty rare to score 8 goals in one game, but it was really common to score 1 or 3, which is interesting because why isn't it as common to score 2? Why the odd numbers? So sometimes seeing the distribution can help us bring in some answers or even some questions about the data that we might want to explore further. Our last example today is looking at Brian and Jessica have decided to move and are considering 7 different cities. The dot plots below show their daily temperatures in June, July, August for each of these cities. Help them pick a city by answering the questions below. Okay, so in this one, each dot represents one day's temperature. And that's the high temperature. And so this is city 1, city 2, and so on. So there's 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, good grief, can't count G, cities that they're looking at, and they're really making this decision based on their high temperatures. And so this is over the summer And so they're trying to see, okay, where do we want to live if the high temperatures are this? So our questions here are kind of starting us to look at the characteristics for describing a distribution. And so it says here, what is the most important difference between cities A, B, and C? So if I look at city A, city B, and city C, their distributions look kind of the same here, but what's changing about them, what's their difference here, is where the graphs are centered. And so this graph, I would say this city on average has a higher daily temperature, where this one has a lower one and this one's in the middle. Their distributions, even if we look closer, are actually exactly the same. So the only difference is where they are along this temperature. So I could say, city A here has an average temperature over the summer at 90, so that might be appealing, 70, or maybe around 80. On number 2, what is the most important difference between city C and D? So if I look at C, I have here. Okay, so that's similar to A, B, and C. And then D I have here. So the difference is not the center like it was on A, B, and C, because both these cities have about an average of 80 as their high temp. The difference that they're seeing is the spread. So the spread of the city's temps is going to be what's making those two cities different. Do you like the 80 average? Okay, that could be a pretty nice city to live in. This one's going to give you that occasional day that's 60, but it's also going to give you that occasional day that's 105. So do you want to live in a city that has on average about 80 degrees and it's pretty consistent around 80 degrees? Or would you like a city that has that variance where you get that day where you do get to wear a sweater, or you get that day where you're hitting up the pool or headed to the lake somehow? On number 3, okay, what if we looked at the differences between D and E? Okay, so center, same at 80. Spread, still get that occasional day of 60, still get that occasional day of 105. So the centers are the same, now the spreads are the same. So now what's different about cities D and E is this idea of an outlier. So on city E, there's a couple outliers. This day, maybe this was a tornado. Oh, good grief, I don't want to go that extreme. Maybe this was a rainy day that it just happened to cool down really quick and it went through and then we were back up to around 70s. Maybe this day was a heat wave that came through and then it rained. I mean, I hope it didn't swing 40 degrees, but it's that idea of it's still consistently around 80, but has an occasional outlier. Maybe this wouldn't even happen next year and this one would be the most consistent. So an outlier is a piece of data that is extremely different, statistically different from the rest of the data set. And so we'll talk about how do we identify those outliers, because this is an outlier. I don't think this one's that unusual. Even though it's further out than this dot, it's not that unusual given the rest of the data. So we'll start talking later on in this unit about identifying them algebraically and what does that do to our centers and what does that do to our spreads as well. And then the last question they're considering is what's the most important difference between city C, F, and G. And so if we look at C, it's centered around 80, spread out here. F, well, still centered around 80. G, still centered around 80. They're spread about the same. If we look about spread, this has about the same spread. This has maybe a little bit more spread. But as far as all three, the most important difference, I would say, on this one is their shape. This is going to have centered around 80, but with temps that are going to be on both sides. Where F is going to be 80, but mostly days are going to get warmer than 80. So there's going to be some days lower, but it's more 80s and above. And G this city is centered around 80, but it's going to have temperatures that don't go as high. And so we're going to start describing our data sets, quantitative data sets, with an acronym that helps us talk about all the key characteristics that we would have for describing this distribution. And so the acronym we're going to use is SOX, where we would have shape for S. We're going to talk about outliers or unusual aspects. We're going to talk about centers, so medians, means, modes, and we're going to talk about the spread of the data too. How variable is it? Does it have a lot of variation or is it pretty consistent? Those are all ways that we can start to talk about an overall distribution that allows us to talk about and understand characteristics of the cities, in this case, that we would be looking at, or any other quantitative data set. Okay, on our practice tonight, let me know if you have any questions, and have a good day.